70s, there was a number of Japanese organizations under the NAMCO umbrella that participated in the OMI program. I'm curious if your organization was able to benefit from the technology and the experience, and I'm particularly thinking of the high-speed exploration system that was developed within OMI during that period. And if not, why not?
Yes. High-speed exploration thing, yes, we tried to use it, but we decided that it's no more, or it's useless. Yeah, so the other thing that there's for the mining systems, but people joining the consortium long walk and then came back to Japan. Then after that, we did this big project with mining systems. But yes, and then we completed the thing in 1996. Then after that, everything stopped. So now we restarted again, but anyway, we try to use some parts that still available, for specification, all the things, equipment and things that they made. Then we try to use as much as possible.
Thank you. Other questions? Yes.
Hello. Yeah, actually, in fact, I cannot resist again to actually congratulate you and all. In fact, I've been hearing, after the presentation of China, we are hearing again about the classification of resources. I think it's interesting to see that I think the resource in the area of Japan has been almost inferred resources, as you have said and all. From inferred to indicated, you want to go ahead and all. Are you having any strategies to do, I think, an additional set of graph sampling or a box score sampling or anything of that sort? Or actually, is this the available information is enough for you to, again, to do some kind of a, I think, geostatistical studies, additional geostatistical studies that will give rise from inferred to indicated? If so, what kind of geostatistics you want to employ? Either way, either sampling or geostatistics.
Yeah, okay. Now the situation right now is that we are thinking about, situation. We are analyzing our situation by the statistical way. Then probably that's going to give us some idea what is the how long is the interval for the indicated resources. Then, using that data, we're going to infill all the sampling again. Yes.
Thank you. Perhaps I could just make a couple of comments, if I may. Thank you again for an excellent presentation. One thing I was going to just point out is that mineral resources, the way you had them presented there, compared with the UNFC, it could be interpreted that they had no economic implications, but under the GROSCO system, they can only be called mineral resources if they have reasonable prospects as for economic extraction. A couple of things about the differences between deposits. The 2D characteristic of seabed nodules, it's true, it's not like most land-based mineral deposits, but there are land-based mineral deposits that have that similarity. One is alluvial mining, which is very often just a very thin layer on the surface, and the mining has to follow the nodules almost, or the nuggets, where it's going. The other is that when you're mining underground, sometimes with very narrow veins, you actually do it almost in a two-dimensional way. So there are some analogues to land-based deposits. The last point I was going to make is more of a general one, perhaps for discussion, maybe not at this workshop, but in the future. You made the very good point that the different resource categories under CROSCO don't have numbers associated with them. They don't. It doesn't say whether measured is plus or minus 5% or 10%, and indicate whether it's plus or minus 10% or 20%. The reason for that is that the Crisco template and the similar ones have to cover a very wide range of deposit types, and to try and fix on some numbers, we've tried to do it in the past. It's a very difficult exercise to get agreement, firstly, as to what those numbers should be, given the very wide range of deposit types. Secondly, how you would measure those numbers, because that's different ways to measure them. And thirdly, what scale we're talking about, because scale comes into classification, whether you're classifying on the scale of a very large area or volume or a very small area or volume. So those are the reasons why there aren't numbers. However, I think the seedbed nodule situation is almost unique in that essentially, as I understand it, it's one deposit. One deposit with many owners or many parties with the rights to explore and then hopefully to exploit. In that situation, there may be an opportunity here for the contractors through the ISA to debate what ought to be the criteria for the different classifications of measured, indicated, and inferred. Should it be in the order of 1.5 kilometre spacing sampling, or should it be 5, or should it be 10? I don't know that you will end up with a definite answer, but because we're dealing essentially with one deposit, I think there could be some degree of common acceptance of what would be sensible. That, I think, would be a very useful exercise because it would improve the comparability of the reporting of each of the contractors without imposing any additional constraints or difficulties in the way of the contractors. It's just, it improves the comparability between the different reports that we get. So I'm just throwing that as a subject, perhaps not for discussion in this workshop, but perhaps in the future. If there are no more points or questions, we'll move on to the next one. Thank you again very much. The presentation is by Ifrema, is that how I pronounce it? I-F-R-E-M-E-R. It's almost as bad as Crisco, by Yves.
So, thank you everybody. I'm quite happy to be here and listen to everything. It's interesting to have in a few hours general view of what's happening. So thank you for the organization. So I was asked 1 month ago to try to summarize maybe 30 years of experience we have in France about nodules. So it's a hard story to summarize. I will try to show you not a detailed point of view of the French side about classification. I've learned yesterday with the criterion that I was not an expert on this side. So what I will try to show is some historical point of view and try to place this in a scale, different scale. And starting so starting with historical background, back in the 70s we start with regional prospection, mainly in the economic zone and also in the Pacific. 75, 76 we moved to what I call large-scale exploration, particularly in the Clarion-Clipperton zone. And starting in 76 to 88, local scale, particularly in the central Clarion-Clipperton zone. And with starting of the exploration license in 2001 to 2014, the main focus was on environmental and ecological study together with new geochemical investigation. So a total for this period of about 50 cruises, which is quite a lot. And here at the base you have a summary of this, just to show that in the first stage it was essentially governmental funding, We had quite a good governmental and industry cooperation through the Gemonode consortium in the late 80s. And then we moved back, and we are still now, to the governmental funding. So for the few slides about the regional prospection, just to place the scales. So we started at the scale of the Pacific with starting point for exploration in the French Polynesia, and rapidly you see with the cruise track that we move in the Clarion-Clipperton area, where we did a series of cruises, and cruises, you see most of the black lines here, just to show that we contributed to the definition of this interesting place at the regional scale. So I call this regional prospection again. And we move to this large-scale geological exploration and sampling. During 9 cruises, 1,683 samples with a grid, very large grid of 50 nautical miles. So again, keep in mind the scales. Then we move to the more local scale with what we call the Noria area. The Noria area with 20 cruises and more than 1,668 samples in this area, where we define it here in green what is now the French license area, one of the main part of the French area here in green. So this is the Gemonode period between, say, mainly in the 80s. Then we, in this area, when we started to focus and we had enough data from surface to move to what I call near seafloor geological mapping, using side scan sonar, photo sledge, IUV, or the old generation of IUV, mainly for taking pictures near the seafloor. And also in '89, we had the very first diving operation using a manned submersible in the nodule area. This allows us to make quite a lot of detailed work and sampling, again, to work on a very detailed scale. So, using these different techniques, we define several types of nodule facies. Here I show the main 4 types. Okay, this is not one type. Facies 0 is no nodules or buried nodules. Type facies 1 is irregular with 2 to 5 centimeters in size. Facies B is regular form with diameter of 5 to 10 centimeters, and the facies C is larger nodules up to 15 centimeters in diameter. So we use, and we will use this in the maps I will show you later. So so here in the last part, 2001, we started the license work, mainly, as I mentioned before, through ecological investigation. I will not mention this work. I know there was a meeting specifically on this point at ESA, so many of this data was presented here. But in the meantime, we continued on the field, but also in the lab, to reprocess chemical data. So the French license, just to show the main area I showed before, and we also have another area on this side. But the main focus in terms of detailed work was on the eastern area. Where we have, so in this eastern area, here in red, we have reprocessed digital maps to numerical maps for the C-beam bathymetry. In this area, in 2012, we did with a new generation of multi-beam system a new map with better resolution, because the first map was a resolution of 150 meters, And we moved to a 75 meters resolution with this new map. So again, this question of scale. So we study small-scale variability and anisotropy. This is a very important point to mention. All these different dots are sampling point with a very large scale, but in order to move and to better modelize the nodules occurrence, we moved to a very close spacing line. One is east-west, and we had two north-south spacing line with about 2 kilometers of spacing. So again, scale of sampling. And we use this for modeling. I will show you later. So using these new maps, we also have from the surface ship, we are able to have these backscattered maps where you see some white and black in the two main working area. Here, oops, sorry. Here again, you have the scale, 70 kilometers for this box, and the main working area is here. With, so you see again this detailed sampling line crossing this main area. And so now all this data was used to discuss the nodule abundance using this, particularly these backscattered maps on the eastern side. All the dots represent the sampling area, and on the main working area. So you see here on the image, in the white part, we have white spot. This means that we have low density in, or nearly no nodules. The scale is here, 0, 3 to 6, so lower than 6 for the white color, and the red color up to 27, with a mean about 15 to 18, was on the gray area. So we will focus now, and we have focused a lot of work on this area, where we try to link, to find a link between the topography, the slope, and the reflectivity, and the nodule abundance. And this opens the possibility to map nodules just using backscattered image obtained directly from the ship. It's not from the near seafloor investigation. Now, if we take the main area, so this backscattered maps, we have this deep basin with white patches. Then we have a plateau and a slope on higher ground, on a steeper slope on this side. So through a combination of photo on the seafloor, diving with nautil, and this backscattered image, we are able to map these different nodule facies I mentioned before. The facies A in the white area with no nodules. The facies B mainly on the B and C are mainly whether on the slope or on the plateau on the side. So so I've just said what is here. So the nodule abundance map was also done in this area with different type of color: white 0, orange 5 to 20, or even 5 to 10, or with a maximum in the southern area here of 15. Most of the interesting place with this 10 mapping being located on the plateau. So now if we consider what has been discussed this morning about slope, we have different processing. One, if we consider a slope, and this was considered through the Rafferner group of lower than 12%, so you have this type of map. But if you move to 5%, you have this map, so the black are those areas that you cannot imagine to mine. Then if you combine both this slope and the backscattered images with a different code of color, you can try to decide what percentage of surface you can eliminate using both backscattered with the map we produced before and the slope. So the lower reflectivity wide and the slope above, we choose for this example 7% for this area, which is about 70 to 80 kilometers long. So this eliminates over about 30% of the total surface is lost for mining. And we think that it will be difficult to go lower than 30%. So again, this was discussed this morning. Very important to discuss the question of this slope. Here a small cartoon to try to summarize what are the questions we have at the local, very local scale if you want to mine. So the slope, I mentioned, 12%. Okay, but it's relatively steep. If we consider 7%, so this eliminates 10 to 30% of surface. Then if we consider the deep basin with no nodules, this again is about 20%. Altogether, you can eliminate between 30 to 45% of what we call unproductive surfaces. Then associated with slope, we have the cliff, of course, with up to 80 meters high. And more discrete structure, such as subsecular depression, probably related to dissolution of carbonates, that can be about 100 to several hundred meters in diameter, and that can be a trouble for a mining system. And also elongated depression that with no nodules, where you can also have this problem. So if you want to mine, you have to consider the known structure from the bathymetric map, but also this more smaller structure, and try to combine your mining technology with different lines, trying to maybe cross some of these smaller features, but also so this is detailed work that has still to be done. So the unknown surface lost through this small structure is, for the moment, not known. And so this opens the question about the need for detailed AUV mapping. So now, a few words about the geotechnical measurement. So 86% of the area is siliceous clay, so we can get sediments on the most of the area, with CU peak of 3.5 to 5 at 40 centimeters of depth. And so this is extremely high when you are on hard rocks, on the cliffs and so on. But one point is that this geotechnical parameters can stay relatively low after reworking of the area. So you have to be careful with this geotechnical parameter. So we have soft siliceous clay. The geotechnical parameter increase rapidly with depth, and there can be a dramatic loss of cohesion after rework. Now, near seafloor side scan sonar images, where you can see here the image with about 1 meter resolution. So you see the scale again here, and you see this A area, which is a white patch with no nodules. And if you look at the acoustic profile, so the cross-section through the sediment, there is a level or transparent level here, and this A area is located exactly here. And what we see is that there is a difference in terms of nodules depending on the thickness of the sediment, this specific acoustic facies with no nodules. So all this type of detailed feature, a few meters probably sometime, and not very deep for this system, have to be considered before mining, or even before assessing the quantity of nodules you can mine. So before trying to classify the deposit. So the geological measurement. So in addition, in this A area, here it's an enlarged view, the geotechnical coefficient is close to 0, so it's nearly it's mud, or maybe it's not mud, it's even water. So it's not a place that you can easily work on, even if there were nodules there. Then if you move to the thicker transparent unit, it's relatively soft sediment compared to the thinner transparent unit where the coefficients are higher. So the importance of the geotechnical measurement, here is a summary of what I've just said. Now, a few words about metal grades. Metal grades and resource estimation. We did some simulation taking into account what I mentioned before, the slope and the density of nodules on the seafloor, trying to see what are the surface we may eliminate through this process. So we consider that exploitable fields, you are losing large surfaces. It could even reach, with all the criteria, 60% of the surface that could be expected, which is the model we produced 20 years ago here on an area of 50 to 20 kilometers long. And so the mineable area we define through this approach is about 1.2 to 5.2 in width and up to 10 to 18 kilometers in length. And then the question is, do you collect samples in all this area, or do you try to do some statistical studies? And we have reprocessed recently this data, and just a few words about statistics. The classical way is ordinary kriging, but if you have a long spacing between the sampling, what you have where you have no samples is average composition, the mean values. If you consider the conditional simulation with same set of data, here we had no data, but with this simulation, you simulate what you have in places where you have a better grading and sampling, and the result is much better represent the real spatial variability. So if you apply this two different models to our area, so you end with a kriging of 1 kilometers block with this type of map, with interesting places in this area. But you lost the extreme values, and most of the values are close to the average. On the opposite, for the same place where you use the simulation, you are closer to the data, but the granularity of your model is much better and much closer to the reality. And so this is what we have here in 3 dimension with the kriging system on the 3D map with the sampling, the slope and the density of nodules, and the same map with a better granularity, much closer to the reality. We see that there are no nodules on the deep depression, the white area, and most of the interesting places are in the plateau, away from the steeper slope. So this gives you a better reality view, a realistic view about what you are supposed to find. So a few words about what was Gemonaut report. And so they did quite a lot of work in terms of geological, meteorological environment, collecting strategy and technical specification, pipe study, rigid, flexible part, hydraulic lift, surface operation, ship type, ship transportation, processing technology, technical economic studies. And at the end, 89, the next step should be pre-feasibility or pilot test. And this was not done, and the economic work stopped at this time. So For this study, we ended with some scenario, mining about 1.5 million tons of dry nodules every year at about 14 kilo per square meter. And this was a compromise between three factors at this time: the metal market for the French and European countries, the collector strategy, 350 tons per hour for 250 days of operating day a year, and of course the production cost. The duration of mining was estimated to be for a 30,000 kilometer surface about 50 years at this 1.5 million tons of mining a year. And so we are still trying to model at a regional scale what could be the unfair, what we call the unfair resource at this stage of this specific area. So in '89, the conceptual model was, and the technical study was done for collecting system using the dredging equipment, a flexible cable, a rigid pipe to bring the material to the surface with a 4 pumping system, a semi-submersible platform, and transportation equipment. So this technical operation stopped in '90 before the pilot test because low metal prices, technological risk, and of course funding. But during this study, I wanted to point it, and this was mentioned this morning, that collecting, so they did at this time very detailed economical study where the mining cost was about 27%, transport in Europe 15%, and processing it's 58%. So this was mentioned this morning. The processing, the whole story, is a very important step and has to be considered. So to finish, some conclusion perspective. I mentioned the importance of slope on the resource estimation and the need to discuss. We choose in my example 7, but we have heard this morning in 5. So this can change the evaluation a lot. And non-surface loss due to small obstacles, we need for this detailed mapping. They may have local abundance and variability that need to be correlated with continuous parameters like bathymetry, reflectivity, picture, slope sedimentation rate, and so on. So this needs IUV detailed mapping. We have seen some examples this morning. And of course, detailed sampling at the right scale. Resource upgrade, so inferred resource for the moment, we call this then inferred, may support decades of mining. So upgrade this level of knowledge for the whole area in terms of sampling and detailed work. Maybe it's not necessary at this stage if you have a good modeling in your hand. And so the detailed evaluation of the resource, the mining strategy, the environmental strategy during the mining needs to produce a high resolution, I mean about 1 meter or less, mapping using acoustic imagery with a new technology coming out with deep IUV. And of course, all this story needs a pilot or pre-pilot mining test. Okay, this is the story I wanted. So it's not a long discussion about classification, but my message is about scales, and classification needs scales. Thank you.
Okay, I think the caterers were sending us a message there with turning up the lights, but we are running up against lunch, but a very good presentation, thank you. Are there any questions? I'm sure we could probably have some after lunch as well, but are there any now? Yes.
thank you very much. Give another very good presentation. I also wish to stress again that it is really important to have this general overview. So I would ask you about, probably I missed, but you had a topic about the grade, and I didn't see any metal content on the nodules. I also would like to know if, because you identified several faces of nodules, if there are any correlation between the grade and the faces, and if there are different, because you did a lot of ecological work, if there are different ecosystems or different modifying factors that can be put in place and put some constraints on the different faces to mine. And also I would like to ask you, because you showed, for instance, for the geotechnical studies, a publication from 1992, the collecting mining system development stopped at the 90s. So I mean, I don't know if France wants a prolongation of the contract for exploration, but I would ask you what will be your perspective. You already showed some, but what will be the strategy in order to improve our knowledge about the resource? Because of course you stated the costs to do that and the lack of funding, and so I just want a reaction from your side to
Okay.
Thank you.
It's a lot of questions. So the first question was about the grade. So the grade, as I mentioned on one of the slides, we had about 1.3 in copper, 1.37 or something like that in nickel. So it's quite interesting. And what we learned, so we can have change in the grade, but in general, it's not a major factor. The major factor is density of nodules on the seafloor. The grade is changing a little bit, but not as much as density of nodules on the seafloor. So if you want to make an assessment about the quantity of copper and so on, the real factor is the change in and the detailed mapping at that I showed. We had the chance to have quite early in this story the nodule mapping, and we need to produce this type of detailed maps and according to these maps to do the detailed survey. So now the last part of the question, maybe I missed a middle, but the last part is what we should do next or something like that. My feeling, and it's a general feeling, not only for nodules, because my main field is sulfide, but is that for scientists, I am a scientist, but for mining industry, you cannot work anymore in the ocean with old maps, even 50 meters in resolution. I moved to this high resolution map 6, 7, 8 years ago, and when you produce map with 1 meter or even sometimes 50 centimeters of resolution, I am originally a land geologist, so I've done a lot of land geology with my hammer. And I say, you see, your scale, again, the scale is your hammer and your eyes. And with this new map we can produce, you can play this in 3D bathymetry, you can pass on the bathymetry, the imagery, and so on. And what you see is what you see when you're in the field as a geologist. So you see the reality. And to go further in this evaluation of nodules for geologists, but also, again, for the technology, to define the mining technology, to define the mining strategy, you need to have this 1 meter or less than 1 meter scale. Of course, the sampling strategy should be correlated to this scale. This doesn't mean take one sample every meter, because when you want to mine, you will have to take another sample before mining. But okay, it's again a question of scale. So what I should do, what I would do if I had the possibility to bring a ship to this place, is to continue this detailed work. Of course, you cannot do IOB on the whole area. So you have to move through this statistic way of grading with detailed granularity with different type of statistical operation to select those places where we should have this detailed mapping operation. Long answer for a long question.
Thank you. Yes, Caitlin.
In the discussion of your mining area, it appears that you had a significantly larger loss and a smaller fraction of mineable area. As I understand it, there are three components of that. One is the area that's unmineable because of the slope, that's unmineable because of low metal content in the nodules, and the appearance of obstacles. It looked like the loss might be larger than the reports because of a larger area of either low or virtually no nodules. Is that correct? And mainly I was wondering if your area is significantly different in topography and distribution than some of the others.
Yeah, I've noticed this morning. I had the data on my slide already, so I don't want to change my data, but it appears that there is some difference in terms of tectonics, number of faults, spacing of faults. So to really compare, we should put the map at the same scale with the same. It's sometimes difficult to compare the map. In addition, the resolution is a very important part, because if you consider the very first map we have in this area, about 125 meters of resolution. If you have a steep vertical slope, this gives you, on the processing, if you have a grid of 125 meters, this gives you not a gentle slope, but gives you a slope, not a cliff. Okay, so I don't know what are the, maybe we have pessimistic, but I don't know. But to go further, again, we need this high resolution map and maybe compare from one place to the other.
Thank you.
Okay, Ted, and then I think we'll probably have to break for lunch at that point.
If I understood him correctly, our last speaker indicated that he did not have any confidence in acoustic backscatter as a means of measuring abundance, or at least specifically from a system that was developed in the 70s. And yet it looked to me like a very significant majority of your assessment of the resource was in fact based on acoustic backscatter. Could you just make a comment on that, or talk a little bit about your confidence in acoustic backscatter? How,
so we have, of course, we have tested this on the place where we have the dive. We have a high density of data, including the side scan sonar. So at this place, as I show, it works relatively well. But this backscattered data have to be correlated to the similar backscattered maps, but not from the surface. What I show from the backscattered part was from the surface, from the ship. When you produce a high resolution map, I mentioned before, you produce again a backscattered map, but with a much better resolution, a few centimeters, a few tenths of centimeters. So then you are at the right scale. So we need, when I mentioned, we need to have this high resolution mapping in the area you wanted to really evaluate and eventually mine. We need to have this and see if the correlation we see in some places, like in our places, can really be used. I would be much more confident in the backscattered and the high resolution maps, the near seafloor through IUV. So we need, so the answer is more or less the same, but I'm back to my general comment.
Okay, thanks very much, Yves. Thank you for that talk. We have one comment before lunch.
Yes, lunch will be for 1 hour, but for the last 15 minutes we have proposal from our Chinese colleagues to show the video. So everybody welcome to see video. Maybe our Korean colleagues also will show us. So welcome to the last 15 minutes of lunch for the video.
start the second part of the constructor effort reporting. And before that, I would like to introduce everybody here, Dr. Swani Naki. He's the director of the NIU, the place that we're going to visit tomorrow. Unfortunately, probably he will not be there, but he's here with us, and we thank you very much for and appreciate your presence. So now I lead the chairs and take over.
Well, welcome back from lunch. Everyone's ready for 3 more presentations and some chance to learn more about what's going on. We'll be making sure that we watch everyone to catch all your questions. And I think right now we'd like to invite India to come up and tell us about their program, particularly how it relates to reserve estimation.
Very good afternoon to all of you. I'll make a presentation on the Indian effort in the resource evaluation. Okay. Most of the contractors have been exploring for nodules for about 3 or 4 decades now. So all of them come with a good baggage of history. So do we. 26th of January happens to be the Republic Day of our country. In 1981, on the 26th of January, we made a history of sorts when this team, led by Dr. Syed Qasim, recovered the first nodules from the Indian Ocean. But the team also comprised Dr. H.N. Siddiqui, who later launched the project for polymetallic nodules, recruited 100 youngsters, including me, in the age of 18 to 25, and that has done wonders for Indian oceanography as well, in addition to the polymetallic nodules exploration which is continuing. We can also see a young Dr. Naqvi over there with that cap, who is amongst us here, the present director of the institute. Okay, so he's been there since the beginning. Okay, the first recovery of nodules made a splash in the news because it heralded an era of deep sea exploration capabilities of the country. These are the basins that were available in the Indian Ocean where the potential for nodule formation was there. And then we chose the Central Indian Ocean Basin because I produced a scanned document of the map that we made in the 1980s to find out which would be the most appropriate basin for exploring nodules in the Indian Ocean. So if you look at a close-up, and then we chose the Central Indian Ocean Basin 3.5 decades ago, and we don't regret it. These are some of the milestones in the exploration saga of Indian subcontinent. The first nodule was collected, as I've shown you, in April 1982. We had the honor of being recognized as a pioneer investor. December 1982, this is what happened, and August 1983 was a good milestone for us because there were so many agencies involved in the nodule exploration and the processing as well. So the first nodules first metal from the nodules was extracted, and about 2 million square kilometers were explored in the Indian Ocean. In 1987, the pioneer area was allocated 150,000 square kilometers, and 94 we relinquished 20% of the area, ratified the UNCLOS, and 1996, 10% more of the area was relinquished, and sampling rates block reduced to 12.5 kilometers, or maybe 1/8 of a degree. And in 2002, 20% of the final relinquishment area. Then our efforts were concentrated towards identification of a first generation mine site, and then in 2013, an identification of what we call as the test mine site, a single block of 1/8 of a degree, where the further activities would be concentrated. I'll explain all these things. But first, I'd just like to show you this crowded slide of the quantum of effort that we put in the work that we've carried out. The total area surveyed in the entire Indian Ocean is about 3 million square kilometers, because we were the only pioneer investor, and then we had to narrow it down from an entire basin or an entire ocean to a small area. So this much an effort had to be put in. And then in that effort, we had sampled out 2,500 locations, and in each location, 5 to 7 operations were carried out using mostly the free fall grab, because that gave us a robust average of a particular spot that was sampled. And then the total number of operations to date are close to 11,000. And then we, starting from a grid of 1 degree, half a degree, and then 1/4. And then finally, we did sampling at 14 kilometers and 7 kilometers grid in a part of the area measuring approximately 18,400 square kilometers. This enabled us to identify the FGM. And then there was metallurgical labs involved in metallurgical processing and trying to identify the routes for extracting metals from nodules. Therefore, we collected about 300 tons of nodules and have taken 50,000 photographs of the seafloor using deep towed systems as well as spot sampling systems. And echo sounding at 12 and 3.5 kilometers for penetration and subbottom profiling as well. 500,000 line kilometers on multi-beam swap bathymetry. This was in the 90s when there was a change in the exploration systems. So around 300,000 square kilometers of area was done by multi-beam swap bathymetry. Then we felt the need for high resolution multi-beam swap, and 12,000 kilometers was done. 50 stations were cored and 76 expeditions in 8 of these vessels. In addition, there was a strong R&D component that grew in the institute, about 350 publications and 25 plus PhDs, and many more are ongoing as on today. So this is the density of sampling that we've done in the Indian Ocean. This shows a kind of a convergence from a large grid to an area which is most interesting and perhaps the richest in the Indian Ocean here. These are the 4 aspects of resource evaluation which I think everybody in this room is fully aware, and abundance, grade, topography, and this thing. So these 2 reserve estimation, they tell us how much is there. And then the topography would tell us how much is mineable. Earlier it was a single beam echo sounding, then subsequently graduated to multi-beam swap bathymetry, and these are of course photography and acoustic methods which are indirect methods of estimation. We use spot sampling in most of the areas using this particular sampler. I think everybody in this room must have done so many expeditions and are familiar with this sampler. As I told earlier, we used to lower 5 to 7 because this allows you, gives you an economy of operation, because at every, in a particular spot, if you want to deploy 5 particular graph samplers, it would hardly take 4 or 5 hours, whereas one which is tethered or lowered by a wire would take equal amount of time. So at the same amount of time, we are sampling about 5 to 7 different locations. The graph is lowered with the help of the weights. Over here, they sink it to the bottom, and the buoyancy pack would bring it up after closing the graph. Once it touches the seafloor, it is collected by a net. Spot sampling was done using Edison graph, and the Russian designed Okean graph as well. And then this would help us. This would kind of give us an assurance that the seafloor has been sampling, because we are sure of the sample, unless an FFG or a free fall graph, where even if it closes and comes back, we are not sure if it has actually sampled the seafloor or has done the closing prematurely. Okay. So this is the thing. And for bulk sampling, we use dredges, collected over 300 tons of nodules, dragged along the seafloor, and that sample was collected in this particular manner. Echo sounding and subbottom profiling are an integral part of surveyor, and then before 1990s, we used to do the single beam echo sounding, sometimes using 3.5 kilohertz. That would give you penetration and find out the sediment thickness as well. And in 1987, all this data up to that time enabled us to identify a pioneer area and a reserved area which is allocated to us, and these are this thing. So all subsequent efforts were undertaken in the bio-focused and undertaken area. Here this is the ISBA current map which shows these areas in the Indian Ocean along with the relinquished portions. Okay. In the 1990s, we did multi-beam mapping, and that was a game changer. And then using multi-beam, we came to know there are so many seamounts in the Indian Ocean. Plus, there are hundreds of kilometers of areas which are of plain topography. Okay. So in each of them, I'm just showing a low resolution map, because that was the technology available in those days. But the multi-beam swap-batic maps in different parts of the exploration area. So after mapping, then the mapping helped us especially relinquish first 20%, because then we were easily able to identify the relinquishable areas in terms of the bank topography. Okay. Subsequently, before the second relinquishment, we undertook, we changed the grid size to 0.125 grid, and 1,025 samples, the stations were occupied in this manner. Then the chemistry was done, grade was analyzed. It's 132 samples, and that would enable us to do the second relinquishment, second 10% relinquishment at this block rate. Then came the task of the final 20% relinquishment. So this was the sampling density and the numbers, and final relinquishment was done like this. So the white portions are the retained area or the exploration area, having 75,000 square kilometers, so two different strips of the Indian Ocean. Okay, so this is the final retained area with the block numbers. The shaded portions are relinquished portions, and the portions shaded over here is the first generation mine site, which is carved out of this ones. How did we do it? We thought we'll first identify a candidate area which is fairly large enough, from which we'll narrow it, and then that we would do close grid sampling and high resolution mapping, because the earlier maps don't have that kind of resolution, to enable to identify small topographic features. And then of course there will be continuous resource evaluation in terms of total metal and total resource available. Okay, so how do we identify the, are we there? Yeah. So the criterion was that the mine site should be able to sustain a process plant for about 20 years, and then should have at least 20% of the area sampled at close grid, that is at a 0.625 or 7 kilometer grid interval, and we should have sufficient topographic information to indicate whether the seamounts or adverse topography or areas of steep slopes. So the first task we identified a portion which is the green, in the blue which is the retained area. So that's having candidate mine site of about 18,400 square kilometers. So this is the blockwise abundances in the area. So why did we choose those 18,000? Because here we could see that we are also interested in looking at blocks which are contiguous, because the concept of a continuous mining system rather than patches of areas of reach. So that was the thought behind that went into this. So we wanted contiguous, consistently high abundances, contiguous blocks, and the highest grade as well in these areas. If you look at the grade, so the metal contents and all that. So this was 18,400, which is the candidate area for a first generation mine site. So in that area, we rather narrowed down the grid of sampling, and then at this we covered around 58 blocks. And then we wanted to do a relative ranking of blocks. We had 411 blocks at 0.0125 grid interval. So each of these blocks was assigned a rating between -2 to +2 for all the parameters. So the net score of 411 blocks was computed using this formula with this kind of a weightage: number of contours, area of seamount, local gradients, and abundance grade between 600. The total is coming to. So we had finally each of this block had some kind of a score, and based on that net score, the blocks were ranked. For the FGM identification, further what we did was that we have 411 blocks with each having a net score. So divide them into these kind of 4 groups, 1 to 5. So we got 53 blocks in that direction, and 6 to 10, 54 to 23 and 54. So these many blocks in these kind of boxes. So after color coding the blocks, so what we did was we give them different colors so that we have a visual estimate. When we look at the area, we know that this is where the clusters are occurring. So clustering was given prominence. And then this is the figure we got. So we have a bunch of yellow clusters, which are the best blocks in the entire retained area in this particular portion. Okay. So these are the. This was the first generation mine site which we identified, and this is the bathymetric map of the first generation mine site overlain on this one and all that. You see that most of the seamounts are falling, or the bad topography areas are falling outside of the FGM. This is a DTM. This is a digital terrain DTM of the first generation mine site. There is an exaggeration of vertical exaggeration of 12. So please don't be worried about the sharp seamounts and those granulations that we are seeing over here. Okay, but this is I can still say that this is work under progress, and we are getting better software so that we'll show the portion much higher resolution. So, This is the high-resolution maps of the first generation mine site. I'll show 4 of these maps from the 4 sites of the FGM. As you can see here, 1, 2, northwest, southeast, and southwest. Okay. Yeah. And then we have done videography and photography using more modern techniques than in the 90s. I think we have seen over the three decades of exploration several changes or generations of technology change, which have helped us to define our areas better as we continue to work in the Central Indian Ocean Basin. So this is the area where also the engineering tests were done for shear strength and other things. And this is one of the blocks showing the thick carpet of nodules. This is another block. Okay, there are some of the seafloor photographs of the area. And then we thought we'll zero in on one single block of these dimensions, so that all further work would be carried out over there, including the environmental impact assessment or the more detailed sampling, or maybe further narrowing down on ROV work or whatever it is, so that we have planned. So that would be done in one single block in this area. So the criterion for ranking was again weightage, very high weightage was being for bathymetry, and then grade and abundance. Since anyhow this is the first generation mine site, we have very high grade and abundance, so they were given 50% of weightage. Okay, so then we did a DTM of all the or most of the blocks with the existing this one. So here also. I think the geologists over here would appreciate the granulations in the seafloor, which are the interplate compression against the Indian plate, but then the exaggeration is so high. So these are all flat areas of individual blocks. You have a 6 times vertical exaggeration factor. This is just a concept to show that everybody is aware of the DTM. But when you finally get around to mapping out the mine tracks, I think the DTM would be of much help, provided data would have much higher resolution than what you have today. Then, so this block out of the FGM is identified as the TMS, and where further activities would be concentrated from here on. I'll just take a few moments for the mining technology development. Okay, we have different institutes in the country which are specialists in different areas. The NIOT in Chennai is doing the mining technology development for nodule mining. Okay, the technologies they developed is first is 500 for scaling up has been done, first starting at 500 meters, and collector and crushing system for nodules mining in shallow water, and then they have developed an unmanned ROV which was tested at 6,000 meters water depth, and then in situ soil tester for which I have shown a picture, and then they've got the results for the soil test they have done. And yes, this is work in progress. Integrated deep sea mining system for mining of polymetallic nodules at 6,000 meters water depth rating. So what have our colleagues done? So in order to realize the pilot scale mining stuff, they thought that it has to be stepped up. So the first capability test was done at 500 meters in the Indian waters using this one. So the performance of the systems was satisfactory enough and gave us the confidence that we can shift our efforts or scale it up to the deep sea thing. And then in the process, an excellent vessel has been obtained which would facilitate all this, Sagar Nidhi. Okay. And then these are the components that go into that. I think most of the people involved in technology know that it's a fairly complex operation. We have a collective crushing system, undercarriage, and hydraulics, buoyancy packs, electronics, and control systems. And then we also, when you're testing in the continental shelf, you don't have nodules over there. Therefore, you also have to design a nodule layer kind of a system. It's good enough to do it in a pond in the backyard of the institute, but then when you're doing it in the field. So there was a nodule laying apparatus which was also designed. So nodules were laid and was used and for nodule laying and tested off the Malvan coast of Maharashtra, about 512 meters depth in September 2010. So a 500 meter mining testing system was also launched at that depth in the Angria Bank at 512 meters depth. Okay. So this is the infrastructure that was developed for all these facilities. You have a hyperbaric tank which can simulate maybe 5,000 meters water depth, deep sea floors, and then in situ soil tester. So this is the data of the soil test that was done first time in the Central Innovation Base, which was done in situ. Mining program, yes, CIB 2011. So the soil tester was tested successfully at 5,400 plus meters in the Central Ocean in 2011. And then the indigenously developed subsea motor was also successfully demonstrated during that demonstration, and then the subsea termination assembly for the soil was used for the first time at this depth, and it is qualified for that kind of depth. Yes, this is work under progress. Sorry, not this one. We are testing a deep ocean ROV. Yeah, this has been successfully tested at 6,000 meters, and these are some of the data that is realized from there, which has been published as well. A deep ocean rose up 6,000, it's called, for developed and tested in the PMN site, in the FGM site, one of the blocks at 5,000 we developed, and it's been tested. So design phase initiated, we design calculate drawing for various subsystems, and acoustic position and other things at 6,000. Initial testing of the hydraulic closed circuit pumps for 600 bar pressure with the baric chamber has been tested. So, sorry?
You have 3 minutes.
I have 3 minutes, so I'll take 1.5 minutes for EIA, another 1.5 for questions. Thank you.
No, it's absolutely okay.
Okay, that reduces my question time perhaps. Thanks. Yeah, we have done a little bit of work in the EIA as well, so I'll just quickly run through that test so that most of that 3 minutes with Sudhakar and Walker we can use for questions. Yeah, the basic concept behind this thing was to establish baseline conditions, potential environmental impact, and understand the processes of restoration most importantly, and then to prepare an environmental impact statement if possible. So these were the studies that were conducted over the last approximately 2 decades, baseline data in the environmental disturbance site, and there are also preservation reference site, which will help us understand relatively what is happening in the distance. And the benthic impact experiment was conducted in 1997-2001, monitoring the impact from this period to this period, almost a decade, and variability study was done from 2005 to 12, and then baseline impact studies in the test mine site, which we have identified recently, will be completed in the next year. Okay, so these are the parameters done. Sediment sizes, water content, shear strength, sediment geochemistry, all fauna on different sizes, micro, bio, and bacteria as well, and currents and sediment flux. We've taken a large area for collecting of these kind of parameters: meteorology, temperature, salinity, currents, bottom currents, productivity and chlorophyll, chemical characteristics such as metal, dissolved oxygen, and particulate oxygen. Particulate organic carbon, sorry, dissolved oxygen, carbon, yes. So the collection of baseline benthic data at 64 stations in 5 candidate test and reference sites. So this is the map which I've been showing throughout my presentation. The tests were done in these areas, as you can see, in and around these areas. Okay, 26 stations. And then the simulated mining experiment was done in 1997, where about in the Indian Oceans, about 580 tons of sediment was suspended in this area, and then yeah, we have the disturbance site is over here, and then sediment traps were lowered in this area to monitor, collect samples regularly to monitor what's happening in this one, and sediment cores in these areas, and CTD and water samples. Okay, so this is the disturbed area. Seafloor alterations in the seafloor conditions are monitored inside and outside the site. Elemental compositions are analyzed throughout. And also just to check if nodules are hiding any important fauna, nodule associated fauna. This is also done for 109 nodules from this one organs. So they all have some kind of small worms or fauna associated with them. 30-20% of them have them. The neofauna, nematoda, and this last year I think there was a conference which detailed all these items. And yes, finally modeling of currents and sediment bloom dispersion is carried out. So what are the conclusions of all these ones? So the environmental conditions seem to vary over different time scales, seasonal and annual, and a wide range, but always follow a particular trend near the seafloor currents, and they are very slow and they are in gyres. The implications is that these could well encompass the changes in the natural conditions of this thing, but as a result, major environmental impact is not expected. I think they should move this very forward. So these are the conclusions of the study. And the major outcomes was, yes. assessing the potential impact of nodule mining on environment, test and reference areas, benthic conditions, natural variability, and environmental data from nodule mining. So these are the data that would go into the nodule mining. So these are the major outputs. These many publications and journals, and these are the databases generated, and all of them have been submitted to the ISPA. If I may discuss them. And thank you. There is one small supplementary information from Dr. T.R.K. Singh, whom I invite to come over. Meanwhile, yes, you can just frame your questions. Dr. Singh, please.
Thank you, Dr. Shamsad. First, just to sum up some of the points which Dr. Prasad mentioned, just to ensure that the focus on the major points are not lost. Number one, NIO was identified as the nodal agency by the Government of India for exploration of nodules. But within an year of starting the work on nodule exploration, an independent engineering consulting company was associated with this program right from the first year. So the point I was making yesterday was that in India, for the government managed projects, we associate an independent, competent organization that works as, just like what you say, competent person. NIO did all the work, it was the boss, but the reporting, the estimating, or the formulation of QC protocol, or the reporting, it was not signed by NIO. It was always signed by the engineering consulting company. So, just to make sure that it's an independent agency that actually submits the report to the government. And this is the same thing for the land-based mining as well. The company does the physical work, but eventual reporting and estimating is always by an independent engineering consulting company. Just to sum up, for the 75,000 square kilometer area, the work completed stands at 12.5 kilometers sampling rate. 30, it's okay, in that range. Part of the area sampled at 6.5 kilometers sampling rate. So that's one. We have measured the shear strength of the sediments collected from the sea floor, a number of them, but we have, in addition, as mentioned by Dr. Prasad, was also carried out in situ test. So that's important because that's a prerequisite information for designing of the mining system. Continuous bathymetry survey for the entire 75,000 square kilometer area has been completed. Dredging of perhaps more than 40 tons has been completed to allow the process test at pilot scale. I'll come to that. Now, as far as the EIA is concerned, the very large area was covered to capture the temporal as well as spatial variations, number one. Number two, disturbance was created and pre-disturbance data was established, baseline data was established, and subsequent monitoring over years was done to look at the impact of these disturbances. This gives us a basis for sort of evaluating future impacts of the kind of mining operations that will be carried out. As far as mining is concerned, we have tested at 500 meters the collector mechanism, the crushing and the transport of the nodules from 500 meters based on artificial nodules. With this step, the next step is, as Dr. Prasad mentioned, for the selected test mining block, the test mining system will be, the mining system will be tested, particularly for ensuring the efficient collection mechanism. We are targeting, of course, eventually the integrated part, but our immediate task is to ensure that the collection mechanism is a reasonably efficient one. Processing. Well, more than 13 processes have been tested in different national laboratories. Eventually, one process route was tested at 500 kg per day scale, a fairly large demonstration plant. And as a result of which, we have design data based on which we could upscale. But the engineering consulting company says that the data generated is fine, but it's not scalable to the commercial scale still. And therefore, this, more work you do, more questions are raised. And therefore, we need more work to get refined data. Because eventually we have to go to the engineering phase. How do we go there unless we generate the design data to suit that requirement? Now, when we did the pilot testing, we recovered only 3 metals, copper, nickel, cobalt. But it was understood subsequently that perhaps for many reasons, 3-metal project will not be, not only it may not be viable, there will be a serious problem in execution of the project. I must say that the integrated nodule project is sort of overlapping, it goes through overlapping regulatory regime. As long as we are in the ocean, we are controlled by the regulations of the authority. The moment we are in the land, then national legislation prevails. And look at, 3-metal recovery plant. Virtually, if you are going for a 3 million ton project, virtually 3 million ton of waste will be stored. And the land acquisition legislation that is available today, it is very unlikely that the government will permit, just 2% recovery of the 3 million ton and store rest of it as a waste. Therefore, we decided that we have to go for the 4th million, and we have then carried on forward the production of manganese alloys, and which is being upgraded to the pilot scale as well. Now, I come last to the classification process. 2 things. I think one of the points that was made is that none of these systems are specifying the confidence limits required for classifying a resource into different categories. My suggestion is, in case of nodule deposits, it is doable. And therefore, it's time that we all agree that the specification of the relative error, or at let's say 95% confidence limit, be specified. My suggestion will be to specify less than 10% for the measured category, 15% for the indicated, and more than 15% for the inferred. But this is just a thought. Now, in case this is accepted, we have had a look at the extensive work that was done on geological modeling for CCZ and also for CIOB in the Indian Ocean. My assessment is that at the level of 75,000 square kilometer, I'm talking about size, 75,000 square kilometer, if you have done sampling at a grid of approximately 15 kilometer, you get an accuracy of plus minus 10%. Even if you take just the arithmetic mean of the abundance values, and grade will be still better. Grade will be probably much higher than plus minus 10%. And fortunately, it is irrespective of whether you are in CCZ or CIOB. As long as you are doing 15%, in both the cases, you will be less than 10%. So, if that is the case, perhaps quite a few cases where the sampling has been done at 14 kilometers would qualify for measured reserve, provided we don't introduce the bathymetry part into the system, because we had some difficulties in sort of mapping the bathymetry part and slope angles, but I'm keeping that aside for the time being. Considering only the quantum and the grade, I think 15 kilometer spacing qualifies for a measured category. Now, yeah, the last point. There is a need to look at the second point. That is, one is the largest scale, the 7. Do I have 1 minute?
Yeah.
Okay. 75,000 square kilometers is one size. The next level, in my reckoning, is 10% of that area. Now, why is 10%? Because 10% of the area will have sufficient resource for 20 years mine life, 20 years process plant life. You can feed 20 your process commercial plant for 20 years. So it could be one area, it could be an aggregate of 2-3 areas. Now, to qualify that small area, 10%, to fall into measured categories, my calculation shows you have to go 5 kilometers or below to come to a level of plus minus 10%. That is all I have to say. Thank you very much. Thank you, Dr. Sharma. We can be together.
Any questions, please? Suggestions?
Thank you very much, and we'll take about 10 minutes of questions. So if anyone would like to ask a question about the presentation or things that you want more information on, please raise your hand.
Well, thank you very much. Again, thank you very much for this presentation, a very good one. And it's just a comment. It is what just you pointed is very important in order to reduce the waste and to go also for manganese alloys. Because in fact, with these resources, we are dealing with the common heritage of mankind. It is also our interest of the authority to have contractors that take the more profit and usage of these resources. So thank you very much.
Excellent. But let's also be careful. It's important, both international point of view or also the national point of view, to use as much value that can be extracted. The problem is residue, leach residue is a very low grade material. And it's a tough job to really get into an economical process where you can convert this residue to manganese alloys. Thank you.
Excuse me. This is a comment as opposed to a question. One of your photographs showed a sled device on the back of the vessel, the benthic disturber. That device was made by a great little company in Seattle, Washington, I would add. But my point is that sled was used by this group. It was also used by Interocean Metals. It was used by the Metal Mining Agency of Japan. And it was used by NOAA to conduct benthic impact experiments. That device is still owned by NOAA, and it's sitting in a warehouse in Seattle. NOAA has indicated many times over that any organization interested in ocean mining that wants to do a benthic impact experiment can use that device at no cost. Right? So for other organizations that haven't done their experiments yet and they want to use it, it is available. At least it was the last time I was in that warehouse. And my only other comment on that is it has not been used since NIO used it in 1997. So you'd have to spend some money to get it back up to working condition. But that, that aside, it's still a good offer on the part of NOAA.
Thank you, Dustin. That's a wonderful suggestion.
Thanks for the presentation, and I think mine also is a comment rather than a question specifically to the Indian contractor presentation. But I'm just reflecting now that of the presentations today from our pioneer contractors, we've had something like 6 or 7 presentations, each covering a contract of something like up to 75,000 square kilometers of the area and zone, and work carried out by many people over a period of at least 15 years, and in the case of 1 or 2 contractors, many more than the 15 years of the current contract. So we've heard about an enormous effort put in. And in terms of the purpose of this workshop, on the whole issues of standards and classification of deposits, I think I'm beginning to hear some common messages coming through, which I've not heard quite so clearly before. And I just make reference to one which you just made at the very end, and that was you wanted something like 10% of the area, 7,500 square kilometers, to be able to go for it for up to, I think you said, 20 years. That resonates very well, and I hope it's not collusion, with our colleague from Dord, who said earlier today that he was looking at 6,000 square kilometers for a period of 20 years. Right? And he went even further to say that that meant he was going to be recovering, or needed to recover, something like 10,000 tons per day at around about 10 kilograms per square meter. So I think we're getting, unless I'm mishearing some of these messages, we're beginning to get some numbers on what might be the inferred to indicated and so on, if we're going to follow the CRISCO methodology, at least as an interim, to take us forward into the next phase. Thank you.
Any more questions?
Thank you for your presentation. I very carefully listen to the scale for the protection, how large area can support economic professional mining program. And I remember it's very careful to discussion during PLEPCON and even during the deliberation of regulation for the modules. I still very careful because we have a formula how to calculate this the size of the area. But this depends on maybe the different the quality and the quantity of the captured area, and of course more important maybe in the future efficiency of the mining system. So I'm still that consider very carefully for this formula.
Can I respond to this? I hope you're talking about the 10% that I referred to. Well, it's just an order of magnitude number, and obviously the selection of this 10% would be one of the best parts of the entire 75,000 square kilometers, and therefore the average abundance will be higher than the average abundance of 75,000 square kilometers. Therefore, my assessment is it will, by and large, provide 20 years mine life without any problem.
System efficiency is another volume altogether.
That's right, but taking into account some broad picture, yeah, that's a different point.
Actually, I thought I will add a comment. It is not on the India's presentation. I don't want to do that. At the same time, I feel that I think the interest in Indian Ocean is only India's, as it stands to, the way. I think we had an interaction. I think the entire interest is, I think, hanging around in the species. So we do encourage, I believe, and I was thinking the authority will have applications even for Indian Ocean.
Well, thank you very much for the presentation. We all got a lot out of it. So could we... And now we'll hear from Tonga.